we have the concept of work and energy. That's what this test is going to be like. So you should be familiar with the concept of work. That's what we spent the first week on, just getting what work was. And then we also have two kinds of conservation of energy. We have conservation of mechanical energy and the conservation of energy. So last week we worked a lot on the development of potential energy and kinetic energy as partners in mechanical energy, ending the week with some conservation where there weren't any losses due to heat or any kind of internal external forces. But then this week we now incorporate to the bigger picture conservation of energy where we're including losses to heat and all that kind of stuff. And in that case, energy is still conserved, you just have to watch out where it goes. And then we start talking about isolated systems to show that the energy is conserved. So if you get all your ingredients in one package and account for all the energy, that should be the same number in the beginning as it is in the end. The last problem we just did, we actually have a loss of energy in the system because we're not considering the air as part of it. So we just found out what the missing part was. And so it's a little bit for you to keep track of those things. So I got a couple more problems in the form of what I call physics carols. And I'll just kind of go through some of the steps. The end of the chapters have formulas. So you should have formulas for potential energy, kinetic energy, various formulas for work, and mechanical energy, etc. Let's see how this all plays together. We got a couple word problems here to wrap it up. So you can write it down and I'll...
You don't have too much time on your hands.
I don't. Unfortunately, I've done this before.
Is this how this test is going to be?
No. I did it once on one problem and it blew people's mind. They just couldn't. They got messed up. Yeah, it's not such a good idea. Test inverse is probably pretty
I'm trying to translate this
Into what?
into modern English.
Modern English.
That is relatively modern English.
Except for the German. Oh, I see. Because it's a little bit. There's a full poetic license here. The problem is it has to be sung. So. You ready? All right. So it goes like this. Oh Tannenbaum, how heavy are your branches? Don't ponder the mass it had before, it falls and turns to matches. That branch it breaks and falls below, about a height of 8 feet or so. Tannenbaum, now at the bomb, how fast will it be traveling?
Recorded for future
And now
generations.
it's solid. Not inverse. Sorry. Energy, what is it? What's going on? Your question to yourself tomorrow, or no, tomorrow, Thursday, is the question. I want to find out how fast it's going. So obviously that's velocity. How do we get there?
1/2 mv squared.
So we got 1/2 mv squared for thinking energy, right? And what are we thinking before that takes place?
Potential.
I think potential energy is where it starts, right? Is everybody getting that when answers these questions? So you just get an energy picture of the problem in this situation. So a branch starts with potential energy, falls, has kinetic energy, and we're trying to determine in the process how it's falling. Any evidence, suggestions, indications that we're concerning energy losses, like due to friction or things of this nature? Nothing here really says that there's air resistance or things of this nature. So as a model, we're taking this as a conservation of mechanical energy. This is the kind of thing you want to look for in the problem to make sure that that's not happening. So I'm going to go with the conservation of mechanical energy. There's my physics point. I'm saying, okay, I'm going to go with conservation of mechanical energy. Unless it's, of course, wrong, in which case it wouldn't be. You can write it out in detail, but eventually what this comes down to is that the initial potential area is going to become final kinetic energy. That's how we're playing the thing through. So our solution to the problem involves writing the equation here. That's like physics. Yeah, that's, you know what? That's what AP Physics tests should feel like to you. Because otherwise they feel miserable. But you go, hey, 3 physics points, more. Not done. Encouraged to move on. There is the wondrous don't ponder the mass it has before. What's that about? Don't worry about the mass, because it's going to drop out.
Aha.
Wow.
H is H. Read the verse.
Okay.
It falls about 8 feet or so. So H is H.
Indeed.
And the M's drop. And we solve for V. And did you recognize this is one of those problems where you have no number of inputs, your answer is going to be in the form of variables. And so our rule for that is the final answer should be written in terms of variables that were originally given to you or fundamental constants. So I know this problem is done because the H was put in the verse. It's kind of hard to sing that. And that would be a verse to it. And the G is a fundamental constant, so I know that that's my answer. It's not a bad thing. It's not wrong. It's generally not a good habit, though, to put G in. They say they have written in the rules that you want to fundamental constants. It's not that they're going to say, "Oh, you didn't follow the directions and mark a point off." It's just that it's not. It's actually better for you not to do that. Sometimes things cancel and drop and refine, and you don't want to lose that quality. When you start calculating, you lose the quality. Okay. Second problem.
Did you make these up?
I will.
Post these on YouTube.
Oh, that's why it's called.
Don't give her ideas.
There's going to be an
Recording it.
See, there we go. Like this credit status stereotype.
You should have blonde hair.
Genetic theory of gases. I'm like, what does this more say?
Everybody set? Here it comes. Joy to the world, we launched a rock. 250 kilograms into the sky. We launched it like a mistletoe. I wonder how high it'll go when launched it by a spring. 10,000 was the K of the spring. From the point it's compressed about 4 meters. About this time of year, working energy comes up. About this time of year, everybody's kind of done. So. Here it comes. What are you thinking of energetically speaking? So you have a elastic potential in there. Everybody see elastic potential, the spring, all that stuff. And what else? MGH because it's going to get launched. So I'm getting a lot of potential energy here. I've got potential energy from the spring, then I'm going to send it up, and there's going to be potential energy eventually that's gravity related, and then we're going to have, in the meanwhile, we do have some kinetic. Do you think any kinetic comes into the problem? Well, the nature of energy is kind of beginning to end, so they're not asking for any speed in the meanwhile. That's kind of a hint to how things are going to play out. Let's try it out. Do you think mechanical energy is conserved or not? I don't see anything involved with removing any energies, so I think it's going to be conserved from our setup. I guess I'm writing down the details. And there's my physics point there. So what's the initial energy? Initially, no. It's an elastic potential to start with, and then it becomes gravitational.
So 1/2 K delta swing.
Right. Just a quick thing to connect with. That last sentence there is kind of important. What's that kind of suggesting? From the point it's compressed. It's a lesson about potential energy, gravitational type.
The final height H was 4.
Or is it? That's what we want to get to. This is a question about where do we put the zero. Do you understand what I'm getting at? You should think about that when you're talking your energy and your potential energy. Where is the zero going to be? The way this problem is set up, it sounds like it might be a nice place to put the H at the compression. Because that's what's going to be what we want to know. How high is it above the point of compression? If you asked us how high was it above the point of release, that would be slightly different H. You understand what I'm saying? So it's important for you to kind of set where your zero potential energy is going to be established. And it looks like the way this problem is worded, we'd like the H to be relative to the point of compression. And that's how my potential energy will work out. Is everybody clear what I'm saying there? So there'll be some gain in potential energy gravitational as we go through the launching, and there'll be more as we release the launch, but the bottom line is potential energy up here has got to be equal to its potential energy down here, because there's no loss of energy.
So if you send it like a completely not.
So because you've got the relaxed length or
Would
point of
that
release.
So there would be negative potential energy then?
Yeah, you can have negative potential energy, because remember, it's not the potential energy is important, but the change. So if I go from a negative to a positive, it's the same change, but the reference would be different. All right, so now I'm popping in numbers and solving for H and getting a distance. Here's the second verse. So our second verse. All set? It comes back down, oh what a drag. Turning flat impedes its descent, decreases its velocity, comes right back down at 23. Just before it hits the ground, be careful how you round. Find the mean of its drag before it hits. What do you hear in this that's novel? Drag. It's got drag. Did I hit drag enough in there? Drag. So when you hear that's playing in, the rock shoots up and suddenly comes back down and starts to flatten out, suddenly air resistance becomes a major factor. When it starts to bother to mention that air resistance is a factor, rough patches, drag, air resistance, things of that nature, now we've got to change our perspective on the energy. It's no longer conservation of mechanical energy, but if we take the entire system, there is a conservation of energy in general. So let's see what we got. We've got a mass of 250. From the previous problem, we had a height of 33. It's coming back down. That's inverse, supposed to imply it comes back all the way down. Yeah, what is it? 23. It decreases velocity, comes back down to 23 implied meters per second. That's the problem with verse, is that you kind of drop things out.
You should have made a practice test below, please.
Yeah. The mean of its drag, are you hearing that? We're talking about the force there? So we're trying to find the mean of its drag. And it says the mean because we're not trying to find the force that varies, but the average. Now what does that suggest when I talk about things like the drag and the mean of the force and things of that nature? Does that mean acceleration? Acceleration that could be involved, but I got a better way of dealing with it, and it's a four-letter word. Work. How does work relate to this?
Force times distance.
Force times distance. So that's where it's going to kick in. If I know how much work is done, then that will tell me how much force there was if I know the distance, which I do. So you can't go through the acceleration equations and all Newtonian laws, but energy has a force, another way of dealing with this problem. That's what we want to emphasize in this one. So, we are going to have a change in the energy then. The mechanical energy is going to be reduced by thermal energy lost to drag. And that's done by negative work from the air resistance, and that's the force we're trying to determine.
Is there gonna be multiple choice on this test?
No. Pure response.
Well,
So the initial energy is potential. I didn't take you through that whole analysis, but that the initial potential is gravitational potential, and the thermal is work done by the drag force times the distance over which it's done, which happens to be the height.
so when saying its initial position was like at the peak of its.
Right. So it comes back down. Oh, what a drag! So it's kind of a Wile E. Coyote moment. Solving towards it F, I brought the kinetic over. So the difference between the potential at the top and the kinetic at the bottom is the work done by the drag. And that means that the drag force then, on average, would be equal to that computation. And I threw in all the numbers and got an average. So this problem highlights the conservation of energy as opposed to conservation of mechanical energy when other factors are involved. It also highlights the role of work in energy, and in this case, the negative work done by the thermal energy. Do you see the difference between the first person and second person? Conservation of energy is going up like a missile without much resistance. Conservation of energy as opposed to mechanical because it came down flat.
And then its thermal is just that technically. It's just.
In this case,
Okay.
yeah, you have to kind of think about what's causing it. There's lots of ways that I can introduce energy in. I could have an explosion in the system, or I could have friction taking it out of the system.
And if it's liquid, it's mu k.
It might involve UK normal, might, but then again, if I just had the energies, I could work what the friction was. That depends on the question, what they give you. Are we good here? All right, one more.
Look at how steady this water particle is.
It's the second verse. So you're right, there's no question. You have to see the first verse, you don't get for information, then it's going to require a little explanation.
How many gifts does he have?
It was on the naughty list.
This will be, we'll ask the usual question, how Santa Claus do it every year.
Yeah. Physics explains it up.
A little physics, a little,
That's physically impossible.
Wormhole.
fastest speed of light travel, yeah.
Neutrinos.
Alright, let's start the first part, get information out of it, then go to the second part. You ready? Okay. Alright, here we go. Jingle bells, Santa starts his sleigh. Rangers pull the gissel fuel, cause the friction all the way. Hey. Jingle bells, 3700 Ks all the way. Oh, what fun it is to ride in a flying sleigh tonight. Looking for information before I erase the screen. There we go. That's all we got.
Oh,
Oh no, I'm not gonna fit it.
The constant friction all the way is important. Now the verse. And I'll let you get this down.
Okay. Yes.
Here's the verse. Here we go. Dashing across the snow, across point 4 view of K. Over 300 meters they go, accelerating all the way. Starting off from rest, take off speed 22. Find how